Hey, John here. Let's talk about something called Flynn's Taxonomy. Obviously, this is a Wikipedia page, so please feel free to run back here and reference this for notes, handouts, and follow-up questions and stuff like that. If I do not cover something in enough detail here. Now, the bottom line of this whole thing is that, look, some guy before any of us were born sat down and said, gee, I kind of notice a trend here. And we have these four observations, these four classifications, all right? So let's look at these. This is the whole ball game here. And look at the size of the scroll bar. So this is a nice, small, concise web page. So we can get through this thing really focused and clear, right? So there's these four-letter acronyms, right? Single instruction stream, single data. Single instruction, single data, SysD. Single instruction, multiple data, SIMD, right? Multiple instructions, single data, MISD and MIMD for multiple instructions and multiple data. Let's start with the first one. This is the one that we're all familiar with. You sit down the first time you ever write a program, what do? You write something in most likely an imperative language that says do this, then this, then this, then this, and then you stop. Okay? And when you're doing things, you got your variables and all this other stuff. What happens when that program runs? Does it talk to any other programs? Is there anything else involved really in the machine? Generally, no. It's a single program running all by itself with its own data. It starts up. Maybe it reads files and stuff like that. It could use operating system services, sure. But it's just doing one thing at a time in order until it's done with its own data. That's what they mean. Single instruction stream means one program that does one thing at a time, all right? Single data stream refers to then that the data that is being used by that one single program that's doing one thing at a time is the data for that program, and it's not shared at the same time with other programs or things like that. Again, this is the machine we all know and love when we first learn how to write programs, okay? This should be pretty straightforward. It's just single instructions, single data. That's what that really means, okay? When we get to single instructions and multiple data, it gets a little bit more interesting. You'll notice the word NVIDIA down here in this description. So this describes kind of how a GPU works, among other things, but the GPU model uses this, all right? So what does this really mean? A single instruction at a time is executed, but it's being executed on multiple data streams at the same time, okay? And it goes on to talk about other ways. Oh, you can do this, you can do that. That's not all that critical. Big picture. What does this really mean? Think about what your GPU does. Maybe you don't know. Bottom line, simplest example that I like to use when I describe a GPU to somebody, let's say I have a graphic on my screen, right? Especially if it's a high def or even a 4K. What does 4K even mean? What 4K means is you got 4,000 pixels across this way, roughly speaking, and 2,000 pixels vertically, roughly speaking. That's 8 million pixels on a 4K screen. A regular 1080p screen is a 2K wide by 1K high screen. So that's 2 million pixels, right? What if I wanted to brighten this image? What would I have to do? Data-wise, if I wrote a program that said, I have an image, I want to make it brighter. What do I got to do? Well, I go in the upper left-hand corner and I go 1 pixel at a time. And what I really am doing is I'm increasing a value, a variable, for each one of these pixels. It depends how the card works, your API and stuff like that, and what color space you're using. But the bottom line is when you increase a number that represents either the color or something we call the YUV color space, the luminosity, needs to be increased. Now, again, it all, whether you're going to increase the amount of red, green, and blue color, or you're going to increase just a luma signal, that depends on, a lot of technology and how your card works. Rest assured, bottom line is each pixel has between 1 and maybe 4 different variables that need to be adjusted to make it brighter. That's my point. Do you write a program with a for loop that just goes, okay, for x equals, 0 to 8 million down here, if this was an 8K image, and just, add 1 to it to make it brighter, and then the next, then the next, then the next, then the next, and you do this 8 million times? That's one way to do it, okay? Well, look what's going on here. Single instruction stream, multiple data streams. The way a GPU does it is it says, okay, I got 8 million of these things to do, but its CPU inside the video card essentially has like 10,000 ALUs in it and 10,000 register files in it. It has only one, control unit and instruction, register. It does only one instruction at a time, right? That's the single instruction stream. However, each of those, like say 10,000, it depends on the kind of video card you buy, but 10,000 of these ALUs and register files all at once is not out of the question. That's not uncommon. Relatively decent gaming systems probably have more than that these days. I haven't checked in a while. Bottom line is, if you've got 10,000 ALUs, well, then what you do is you do 10,000 rows all at the same time. So you don't just say x equals 0 to 8 million. What you're doing is you're creating many x's. First x is 0. The second x is, whatever pixel is on line 2. So your first one will be 0, 0. And the next one would be maybe like 1, 0 and 2, 0 and 3, 0, however the coordinate system might work. And then as you go across in your for loop, you don't start here and raster it down and across and across and across until you get down here. You just do this massive march of 10,000 all at once across here. Bang, and you're done. Then you leap forward another 10,000 and you do another group of 10,000 all at once, and so on. So this thing would run 10,000 to 1 faster than if you did it with a CPU. That's why they sell so many of these cards, and that's why literally speed ups on the order of 10,000 to 1 are not uncommon. However, if you think about it, how often you need to solve a problem that is of that nature? Okay, some are very common, and it applies very well, especially to graphics. Like I said, to brighten an image or something like that, or draw a little shape here while you're drawing a little shape over there. We call these polygons or triangles. It depends on how the GPU is set up. So it can do a whole lot of things at once, but all those things have to be the same thing with different parts in the image in this GPU example. All right. This is right now probably the most common SIMD machines out there. They have other ones as well. If you look at the Intel instructions for the Intel, the x86 and the AMD 64 instruction sets, you can do things like create they have like a register file that they don't just have simple registers. Sometimes they have registers in there that are entire arrays, what they call vector instructions. So instead of having one register that might have 32 bits, it might have a register that has a whole array of 32-bit values. Now, usually there's only like 8 or 16 of those in there, but you can say things like add 1. And just like the GPU, the AMD 64 and the x86 instruction sets might add 1 to all of those, like I said, 8 or 16 variables in that little array, in that little vector all at once. So that is what Intel means when you say, oh, I have vector instructions, okay, things like that, all right? Again, that works out basically the same kind of thing as NVIDIA. Why? Because they're all SIMD type instructions. So that's what this thing is all about, right? And you can see a stark contrast to what it means to do single thing at a time with one variable at a time, right? So this is a single thing at a time, but your variables come in massive chunks that all work the same at the same time, okay? Multiple instruction streams and single data. So this is the first time we go from single instruction to multiple instructions, okay? And again, we have our two items. You can almost see a kind of a truth table sort of thing happening here, right? You've got single and multiple, and you've got a single and multiple in this other column. So you actually, it's like binary. You got a 0 and a 1 and a 0 and a 1. You can kind of think, obviously there's going to be 4 different combinations because you have 2 options. Whether you're going to go single instruction or multiple instruction, and whether you're going to go single data or multiple data, okay? Just a little side observation, especially since we've been talking about that for a week or two at the beginning of this semester. The same kind of combinatorics kind of applying here. All right, so what does it mean to have multiple instruction streams all processing the same single data stream? Now, as this points out, the word uncommon architecture is in here. However, I hope that we can all relate to something, and that is that this is generally used for fault tolerance, okay? Like the space shuttle or medical systems. It's been a long time since I've dabbled with this kind of machine, but what happens when you use these is they have basically copies of the hardware, physical copies. So instead of having one CPU that might be executing a single instruction stream with single data, you have a whole bunch of CPUs that are all executing the same instructions on the same data at the exact same time. And what happens is there's some circuitry in there that says if I have 3 or maybe 6 of these or 9 of them all going at once, and they're all doing the same thing, they're actually synchronized at the clock level on a fancy system anyway. Every single gate and every single signal that's coming in and out of the CPU that might interact with the memory or any other part of the system, what happens is they are compared against all of those units. So in the simple case, you got 3 of them, right? What you would do is you say, well, did every one of these 3 things add together these numbers and come up with the same answer or not? And if the answer is no, what happens is the majority is the one that's used. It's called a voting system sometimes, all right? So it would be nice to have several of these, and it's handy to have an odd number so that you can always get an obvious majority. You can never have a tie, in other words. And that's literally what happens. Everyone does the same thing at the same time, and hopefully gets the same answer. And when the answer is different, you go with the value that the majority of all the circuitry decided to go with. And again, you've got yourself a space shuttle or medical systems and stuff like that. It'd be nice to know when your life is on the line, you don't have some cheap, cruddy CPU that happens to, crap out and die in there. Better to have 20 cheap, crappy CPUs because one of them is bound to, keep running. The majority of them should still work, right? So this is where you see this kind of thing, all right? And then we have the last one, the multiple instruction streams and multiple data streams. Again, this is another something that architecture, another one of these that we're probably pretty familiar with. The first one, very traditional. Single core, single CPU, do one thing at a time until you're done. Well, what is this thing? This is the PC on every one of our desktops, your phones, your laptops. This is what those things are doing. How many cores do I got? That's your multiple instruction streams. When we say multiple instruction streams, we're generally talking about different programs, okay? Now, this also could mean different threads within one program, right? If you're familiar with that sort of thing. For the average computer user, what this really means is I can run more than one program at a time. And if I run one, it doesn't slow down the other one, okay? But why? Because I can have multiple ones going. I have maybe I got multiple CPUs, or maybe I got a CPU that has multiple cores in it, so each one can do a different thing. And the multiple data streams simply means that they don't have to share anything. These can be completely independent, not only executing different instructions as they run, but they can be using different data. So I could open up, say, a Word document in an Excel file. They have nothing to do with each other, but they're all running at the same time, and they're not competing so much, unless, your disk I/O maybe because you don't have multiple hard drives or something. And certainly in terms of the compute resources that are needed to run those programs, they run independently. All right, so that's what you've got here. Right? These 4 things. This is everything to do with Flynn taxonomy. Single instruction, single data. Single instruction, multiple data. Multiple instructions, single data. Multiple instructions, multiple data. These are the 4 basic architectures that we get into when we're dealing with the bigger picture of parallelism. How do you deal with multiple cores? Are they all doing different, unique? Can they all free run on their own, or do all of them have to do the same thing at the same time, right? Maybe you don't have a complete core. That's this guy. You'll notice that a GPU, each one of those things, each processing element inside of a GPU is not really independent. They all have to do the same thing. The only thing that can vary is what the data is that they're working on. Like I said, if you want to brighten the screen that you're looking at, right? Each one of them does 1 pixel, but they could all be doing different pixels at the same time. All right. Now they got some pictures down here to kind of illustrate what's going on. We got a single instruction, single data. The fact that they have a data pool over here, this is called a processing unit. I think they point that out here. Good. Thank you very much for defining your terminology. Thank you. My point is this is kind of drawn using a Harvard style architecture, right? In a Harvard architecture, your instructions and your data can, and they are, by definition, in a Harvard-style machine, stored in different memories, okay? Different physical memories that are both connected up to the CPU, okay? You can also think of this as different regions of one giant memory. That's your von Neumann architecture, where the processor has a single memory that has everything in it. And the von Neumann is what we've been talking about so far in these lectures. When it's obvious because, like when I drew up the RV32i core, I had one single bus connecting to one memory. That's definitely a von Neumann machine, okay? So, single instruction, single data, one CPU, do whatever you want. Single instruction, multiple data. Look at the difference here. You have the single instruction coming down to this processing unit. You still have this single instruction. This is your GPU. Only one instruction is being executed on all these at the same time. However, each one of them, like in my example above, could be dealing with adjusting the brightness or the color or whatever you want for different pixels on the screen all at the same time. So these arrows here strongly suggest that these are all doing the same instruction at the same exact time with different data sources, all right? Now, in the multiple instructions over here, you got your what? Multiple instructions with single data, multiple instructions with multiple data. The single data example that I cited was like space shuttle safety and stuff like that. Now, that is a kind of a subset, actually, of this general drawing, right? Let's look at this kind of closely. Data pool has one single line coming out of it over here. Then it splits into two, and then it goes to each processing unit over here. Well, obviously, that means that if a data item comes out of this pool, the same data item goes to both of these, right? Now, this notion of what I described as a subset of a more general definition, it does say multiple instruction. All right. So in theory, this also includes something where this and the other one over here might be executing completely different instructions at the same time, even though they're using the same data. All right. I don't have a good example of that. I've never really run into machines that work that way. But I have dealt with a subset of this where if you connect these two lines together, and even their own example is of that ilk, okay, where you have really, a single instruction happening with a single data, but with multiple processing units that can all vote to see if they all agree that whatever they've just been asked to do is the right answer, okay? So that arguably is a formal subset of what this general class is, right? But as they pointed out up here, this tends to be used, A, it tends to be uncommon, and B, it tends to be used for types of fault tolerance systems, okay? And I know I'm not lying to you because I've actually used machines that literally work exactly like I just described. You buy the module, and it has many of these CPUs on it, and it has all the voting logic and these control signals that come out that tell you whether there's a majority that agrees or not. Sometimes it'll actually get to the point where it says, I can't know. We've had too much failure all at once. And you can then know that that your system has failed as well. Okay, so now we have the last one, multiple instruction, multiple data. Again, this is a very common thing. So the most common, I guess, things that we are exposed to every day is a single instruction, single data. Most of the programs that you write are single threaded, do something from start to finish in order. They work this way regardless of the kind of machine they run on. You don't have to take advantage of all the parallelism in your machine if you don't want to, is my point. The other one that we're all familiar with every day is this one down here. Every processing unit can do anything it wants with any instruction at any time in different data. All right. I would argue this drawing is a little wonky because each one of these should have its own independent line back to the instruction pool. I guess he ran out of marginal space here. OK, but quite simply put, when you buy a CPU for your PC, like mine on my desktop right here, here's I'm working on it right now as we record this video. You can run a program called top. I'm on Linux. This is a command line application that says what's running. We call this is the top of the run queue. What is the thing that's hogging up the most CPU and memory right now? Well, that's FFmpeg. That's what's recording my screen. So it's wasting 40% of a CPU core. If you run this and you press the number 1, what happens here is it opens up and says, of all the cores you have, I got 16 cores, here's what each one of them is doing. Some of them are 2% of the time executing user code. Right? How much time is it spending calling operating system, like reading and writing files? That's this column here. This is something that we're not going to talk about. Go ahead and read the manual for that. And this is how much time it spends idle. So this machine is really idle. Even though I'm using 40% of what would say is one core for one program here. Okay, why? Because it's you add up all these numbers over here, plus all the time it spends in the reading and writing files and stuff like that. It just adds up to about 40% of one of these things. Although the math doesn't look that great. I'll leave it as a test to the reader to understand why. Well, I saw like an 89 down here. As it flips, it's hard for me to scan all these at once. I'll just hit quit and leave that as a test for the reader to figure out why those numbers don't seem to add up at first glance. But Top is a very useful tool to figure out where all your time goes. Windows has a thing where they have meters and stuff like that. You can use that on a Windows box as well for the same kind of thing. All right, so these are the 4 things. You got to remember what they are. It's a rite of passage, right? And normally the people will refer to that as SysD, MISD, SIMD, and MIMD. All right, so in casual conversation, those are how you pronounce those acronyms. The Wikipedia page goes on to further subdivide and make other observations. That's not really something that I'm all that concerned about in this lecture. We just want to understand the basic top-level view of these 4 different classifications, and the fact that 2 of these we use every day, all the time. And anybody that writes gaming software is painfully familiar with what happens when you need to program a GPU. So that's the 3rd one. And of course, if you're a gamer, if you're a user of games, you're using 3 of these 4 all the time anyway. All right? So that's all there is to Flynn's taxonomy. Thanks for watching. See you next time.